In this video, we solve problem 8.4.041 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the definite integral using the given integration limits, and the limits obtained by trig substitution. So we have the integral from 4 to 6 of this function, and they want us to do this two ways. It's a little bit ambiguous from the problem statement what they mean by this, but the way I took it was I interpreted it this way. When they say evaluate the definite integral using the given limits, what they're saying is compute the antiderivative first, get your answer in terms of x, and then substitute in x equals 4 and x equals 6 and see what your answer is. And then when they say do it again, this time using the limits obtained by trigonometric substitution, you're going to get the same answer, but instead of working with x equals 4 and x equals 6, we're going to use the corresponding angles in terms of theta after making that trigonometric substitution. So I'm going to show you how to do it both ways. I'll do this way first, and then we'll do the second one, and we'll see that we get exactly the same thing. So for the first one, the approach is this. We want to find the antiderivative entirely in terms of x, and then plug in the limits x equals 6 and x equals 4 and subtract using the fundamental theorem of calculus. So we'll start by anti-differentiating. And notice that x is greater than 4, or in this case, a squared is 9. So a is 3, so x is greater than 4, which means it's certainly greater than 3. That's important for our trigonometric substitution. So for part A, we're going to evaluate the antiderivative. Okay, so we say this integrand involves an x squared minus a squared. A u substitution doesn't work because if I let u equal this, du would be a 2x dx, and I don't have just an x dx, I've got an x squared dx, I have this extra x, so u substitution doesn't work. Since our basic rules don't work and u substitution doesn't work, we're going to try trigonometric substitution. Since the integral involves an x squared minus a squared, we're going to make a tangent substitution. I think I may have said that wrong. Make a secant substitution. And that's because this kind of looks like our arcsecant antiderivative integral, but it's not an arcsecant antiderivative. If it looks like an arcsecant, but it's not an arcsecant, and basic rules in u sub fail, then we use this secant substitution as a form or one of the types of trigonometric substitutions. So to do that, we start by identifying a squared. A squared is 9. Then we compute a. It's always the positive square root, so that's 3. And then we let x equal a, in this case, times secant of theta. And then we want to write everything up here entirely in terms of theta. So that requires computing dx. And then writing this x squared minus 9 in terms of theta. So we just want to simplify that. I call all of this preparing to substitute. So the idea is, with trig substitution, we're trying to write everything up here in terms of theta. So we let x equal 3 secant of theta, and dx is 3 secant of theta times tangent of theta, d theta. And the square root of x squared minus 9, that's the radical expression in our integrand, can be written this way. Since x is 3 secant of theta, substitute that in. Square the 3, square the secant. Factor out the 9. And then with a secant substitution, this will always happen. We're going to end up using this Pythagorean identity. We know that tangent squared plus 1, or tangent squared of any angle plus 1, is equal to secant squared of the same angle. So if I take this and I subtract 1 from both sides, I get tangent squared of A is equal to secant squared of A minus 1. So this is secant squared of our angle theta minus 1, so it's going to be tangent squared of theta. And in general, this is going to give us the square root of 9, which is 3, times the absolute value of tangent of theta. Now, when x is greater than 3, the absolute value of tangent of theta is just tangent of theta. In general, if x is greater than a, this absolute value is going to be the positive tangent of theta. If x is less than negative a, if x were less than negative 3, based on the bounds in our original integrand, then we would use a negative tangent of theta. And that has to do with the domain and range issues for the tangent function and the secant function and the inverse tangent and inverse secant functions. That's why the secant substitution is just a little bit different in this step than the sine substitution and the tangent substitution are. Okay, so we've prepared to substitute. Now we want to write everything in our integral entirely in terms of theta. So in the numerator, we have x squared. In the denominator, we have that radical expression. And don't forget to substitute your dx as well. Every single piece needs to be written in terms of theta. So x was 3 secant of theta. So x squared is 3 secant of theta squared. Dx is not replaced by d theta, it's 3 secant of theta tangent of theta d theta. And the denominator is just that square root expression, but that square root actually simplified to 3 tangent of theta. Okay. So we're writing everything in terms of theta. This is a part of the step that I call substituting and simplifying. And then anti-differentiating. This is step 2. The whole point of the trigonometric substitution is to get this into a form that we can anti-differentiate. And if you're saying to yourself, oh, I don't know how to anti-differentiate powers of secant and tangent, it's okay if you don't remember, but we learned that in the last section. This will always get down to an integral that can be evaluated using the methods of the previous section, if not use substitution or one of your basic rules. So we've got a 3 in the numerator and denominator that reduces, and then a tangent reduces there. We end up with a 3 squared from there, that's a 9. And then we've got a secant squared theta and a secant of theta d theta right there. Now in general, I would write that as secant cubed. And then I would say to myself, how do I handle this integral of secant cubed? Now, I remember how to handle this, but many students, when they get to this point, won't remember how to handle this. So what I recommend you do is go back to your trigonometric substitution guidelines. Look for a guideline that talks about an integral that looks like this. you've got secant raised to an odd power. So I would go to my trigonometric integral sheet. The powers of secant and tangent are on the second page. And the first guideline says, if the power of secant is even and positive, nope, that's out. If the power of tangent is odd and positive, there are no tangents, so that's out. If the power of tangent, that's out. There's no tangents in our problem. Up, here it is. If the power of secant is odd and positive and there are no tangent factors, use integration by parts with dv equals secant squared of your angle times the differential of your angle. So we know we're supposed to use integration by parts. And dv in the integration by parts formula is supposed to be given by secant squared theta d theta, which I think makes a lot of sense because we know the antiderivative of secant squared. Now remember how integration by parts works. The integral here is u, or the integral of u dv. So part of this is u, everything else is dv. And then in order to use the integration by parts formula, which tells us that the integral of u dv is u times v minus the integral of v du, we need to know what v is. So we anti-differentiate dv to get v back. We need to know what du is. So we differentiate u here as well. The antiderivative of secant squared of an angle is tangent of that angle. The derivative of secant of an angle is secant of the angle times tangent of the angle. Don't forget to multiply by d theta because this is a differential of u. So then according to integration by parts, the integral of u dv is u times v minus the integral of v du. If you set up your 2x2 table like this every time, you'll always just multiply across the top, then multiply across this diagonal, and you're subtracting, and don't forget that the second one involves an integral. You got uv minus the integral of v times du. So we have 9 times u times v. In this case, that was secant of theta times tangent of theta, minus the integral of v, which was tangent of theta, times du, which was secant of theta, tangent of theta, d theta. And I think I'm just going to leave that 9 there for right now. And of course, you can simplify this. You've got a secant, and a tangent times a tangent is, of course, a tangent squared. Now for this piece, you might go back to your trigonometric guidelines or trigonometric integral guidelines again. After doing this a while, you probably won't have to refer back to the guidelines as often, but notice we've got a tangent squared, that's right here, times a secant of theta. So here it is, guideline number 5. If the power of tangent is even and positive, and the power of secant is odd and positive, and that's what we have in this case. Power of tangent is 2, that's even and positive. Power of secant is 1, that's odd and positive. You're going to use a combination of guidelines 3 and 4. So on 4, that's where we did the integration by parts. For 3, it says if the power of tangent is even and positive and there are no secant factors, write one tangent squared factor in terms of secant squared using the identity tangent squared of an angle is equal to secant squared of that angle minus 1. Distribute and split the result into 2 integrals, repeat as necessary. Okay. Hopefully you do this enough that you see this and you recognize, oh, I've got an even tangent function here and an odd powered tangent function here, and secant raised to an or tangent raised to an even power, excuse me, and secant raised to an odd power. So I'm going to replace tangent squared of my angle with secant squared of the same angle minus 1. Okay. Now this is where it gets a little tricky for many students. But once you've seen this trick a few times, I think it becomes, it gets a little better. So what we have is 9 times secant of theta, tangent of theta. And then I've got secant times this quantity, secant squared minus 1. So if I distribute, I have secant times secant squared is secant cubed, and then secant times -1 is going to be a negative secant of theta, d theta. Now, if you're starting to worry, that's kind of a good sign, because that means you recognize the integral that we started with. Remember where we started. We started with this, but after the substitution, we were here. We had the integral of secant cubed. And if you're starting to think that this is circular, that's a valid concern. But it turns out that because of this negative sign here, it's actually going to be really easy to figure out what secant cubed is. I'll show you. So this is equal to 9 times secant cubed theta d theta. So I'm sort of thinking of this as an equation now. If let's reduce the 9 from both sides. Then we'll have secant of theta, tangent of theta here, minus secant of theta, or the integral of secant cubed theta d theta. And if I split this into 2 integrals, that's going to be minus a minus, it's going to be plus the integral of secant of theta d theta equals, and remember I've divided that 9 out on both sides, the integral of secant cubed theta d theta. And that's a basic rule, and that's what we're looking for. It appears on both sides. But this is great. It's actually not circular. If this was a positive secant cubed and that was a positive secant cubed, I'd be worried, because then if I subtracted those from both sides, they would be gone, and then I would just end up with some relationship, provided I had done everything correctly. That relationship should just be an identity, but still wouldn't help us find the value of the integral of secant cubed. But that's not what we have here. What we have is an equation where the thing that we're looking for, it's kind of like a variable, appears on both sides. So if I'm solving this and I'm trying to figure out what secant cubed is, it's actually a lot like solving this. I've got something minus x plus something equals x, and I'm trying to get x by itself. Well, in order to get x by itself, all I would do is add this x to both sides. So then I'd have 7 equals 2x, and then I would divide to get x by itself. That's exactly what we're going to do here. It just looks a little different because of the integrals. We're going to add this integral of secant cubed theta to both sides. And then on the left-hand side, what we have is secant of theta, tangent of theta. The antiderivative of secant of theta turns out to be natural log of the absolute value of secant of theta plus tangent of theta. And that's equal to 2 times the antiderivative of secant cubed theta d theta. Now, this antiderivative, well, it is an antiderivative, it's an indefinite integral, so the result should not just be this, it should be that plus a constant. I'll just call that constant c. And if I want to get secant cubed theta, or the integral of secant cubed theta by itself, I just divide by 2. And in this case, I actually want 9 of those, so I will divide both sides by 2. And then I will multiply both sides by 9, because I want 9 of those. Okay, so now we have 9 times the integral of secant cubed theta d theta is equal to 9 over 2 times secant of theta tangent of theta plus natural log of the absolute value of secant of theta plus tangent of theta plus c. Okay, so that's the trigonometric integration part of this. Now, the way the problem statement was asked, we were asked to evaluate this using the given limits. So the way I interpreted that was I said, okay, what they want me to do is compute this antiderivative, find the result in terms of x, and then plug in the limits x equals 4 and x equals 6, and find out what the answer is. And then show that you get the same answer using the other method. So that means we have to write this result in terms of x. In order to do that, we've got to go back to our trigonometric substitution method. The first thing we did was we prepared to substitute. Then we substituted, simplified, and anti-differentiated. But that result is in terms of theta, not x. In order to get back to x, we have to use this original substitution. We're going to draw a triangle. We're going to use this original substitution to label the sides of that triangle. And then once we have the triangle, we can write the answer in terms of x rather than in terms of theta. So that's our third step in this trigonometric substitution process. So the goal is to write the result in terms of x. But in order to do that, actually, that's not step 3. This is step 3. We're going to draw and label a triangle in terms of x. This is using the original substitution. Now, our original substitution was x equals 3 times secant of theta. So we can divide both sides by 3, and we get secant is x over 3. So that is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So when I draw my triangle with that as my angle theta, the hypotenuse should be x. When the side adjacent to theta, that's next to theta, but not the hypotenuse, not the one across from the 90, when that's 3. And then by the Pythagorean theorem, since this squared plus this squared equals this squared, this side length must be the square root of x squared minus 3 squared. Okay, so we needed secant of theta in terms of x, and we've got it. It was really easy. We've got that right there. And now we can use this triangle to find tangent of theta. That's the other expression in our result in terms of x. Tangent is opposite over adjacent. So that's square root of x squared minus 9 over 3, and we can replace that there. Now, this was not necessary for this particular problem, and I'll tell you why. We actually already knew what secant was in terms of x without drawing this triangle because we could just do that. And we knew what tangent was in terms of x as well because of these steps from earlier. We know that tangent of theta is equal to this square root of x squared minus 9 divided by 3 just from this result. So the triangle wasn't necessary this time, but I wanted to practice with you because sometimes it is necessary. Not for most of the secant tangent problems, but it is often necessary for the trigonometric substitutions involving just tangent or sine, like a tangent substitution or a sine substitution. Okay, so now we can write our antiderivative in terms of x. And remember, this is all going back to that original integral, x squared over the square root of x squared minus 9. And this is equal to this through our trigonometric substitution. And this is equal to that But now we know that secant of theta is x over 3. And tangent of theta is the square root of x squared minus 9 over 3. So we should write that here. Plus c. And if you want, you can simplify. If I distribute this 9 over 2 here, this 9 is going to reduce with that 9, and we're going to end up with 1/2 x times the square root of x squared minus 9. And we have to distribute that to this expression as well. So we'll have 9 over 2 times the natural log of the absolute value of x plus the square root of x squared minus 9 over 3. You get a common denominator. Now, you could leave it like this, and this would be fine, but I could even simplify it further using this fact. Log of a quotient is log of the numerator minus log of the denominator. So this log of this over this is actually the log of the numerator minus the log of 3. And the natural log of 3 plus a constant is just a different constant. So while this is not necessary, with some problems, if you're checking your answer in the back of the book, it might not have this over 3, because what it would have instead is this. If we distribute that 9 over 2, you have a negative 9 over 2 times natural log of 3 plus c, and that's just a different c. I'll just call it c1. Okay, now we're still not done. They wanted us to evaluate this definite integral using the given limits. So now that we know the antiderivative in terms of x, we're going to plug in 6, plug in 4, and subtract. And that's going to give us a certain, well, it's going to give us an answer. And this is just applying the fundamental theorem of calculus. When you substitute in x equals 6, you're going to have 1/2 of 6, which is 3, times the square root of 6 squared, which is 36, minus 9, plus 9 over 2 times the natural log of the absolute value of 6 plus the square root of 36 minus 9. Okay, that's what we get when x equals 6, minus what we get when x equals 4. 4 times 1/2 is 2. We have 4 squared, which is 16, minus 9, plus 9 over 2 times the natural log of 4 plus the square root of 16 minus 9. Okay, 36 minus 9 is 27. And the square root of 27 is the square root of 9 times 3. Square root of 9 is 3. Square root of 3 can't be simplified. So I can replace this with 3 root 3. 3 times 3 root 3 is 9 root 3. Then I've got 9 over 2 here, natural log of the absolute value of 6 plus the square root of 27, which is 3 root 3. And then we're subtracting this down here. And then we're subtracting, so 2 times this square root, 16 minus 9 is 7. So we've got 2 times the square root of 7 there. And then we have a distribute the negative to both terms, minus 9 over 2 times the natural log of 4 plus the square root of 7. And let's see, I've got 9 root 3 minus 2 root 7, and I have this log and this log, which can be combined if I factor out that 9 over 2. This is log of A minus log of B. And we know from pre-calculus that that's log of A over B. Actually, it doesn't do much for us in this case, but it does make the answer a little simpler looking. So log of this divided by that. And you could factor out a 3, but I don't think it would help, so I think I'll just leave that alone. Okay, so that's our answer using the first approach. Oops. Now the question asks us to do it 2 ways, using that approach and then using this other approach. Now the second approach is similar, but instead of doing all of this as an indefinite integral and then plugging in x equals 4 and x equals 6 at the end and subtracting, what they want us to do is actually find the appropriate bounds here. So for the second part, we're going to take this definite integral, we're going to do all of this, except when we get here, we're not just going to substitute and write this as an antiderivative in terms of theta, we're going to substitute these bounds for x to get bounds for theta. And that should give us the same answer. So let's think about it. When x is equal to 6, since x is equal to 3 secant of theta, if I substitute an x equals 6 here, we get 6 equals 3 secant of theta. Divide both sides by 3, so we're going to get 2 equals secant of theta, or if you prefer, cosine of theta equals 1/2. And then when x is equal to the lower bound 4, we have x, which is 4, equals 3 secant of theta. So secant is 4/3, or the reciprocal of that. Cosine of theta is equal to 3/4. Now that didn't give us values of theta, but that did give us values of the cosine function. Now, these 2 equations have infinitely many solutions. We just want one solution. We want one solution to this equation and one solution to this equation. So what I would do is I would solve these on the interval from 0 to pi, because that is the range of values that we get from the inverse cosine, which is closely related to the inverse secant function. So I'm solving cosine of theta equals 1/2 on the interval from 0 to pi, and then I'm trying to find the corresponding value of theta. Since x equals 6 was my upper limit, the corresponding value of theta here is going to be my upper limit down here. And again, remember what we're trying to do. We're just trying to show that we get the same thing either way. We're on the interval from 0 to pi. My cosine function is a positive 1/2. That's adjacent over hypotenuse right here. Well, that's a 1/2 square root of 3 triangle. The angle opposite the square root of 3 is a 60-degree angle. But we're in calculus, so we're going to switch to radians. 60 is 1/3 of 180, so that's 1/3 of pi. When x equals 4, we have cosine of theta equals 3/4. Now that's not a special angle. but cosine of theta would be 3/4 somewhere over here. So when the adjacent side is 3, when the hypotenuse is 4, so I would just say, let's let theta equal the arc cosine of 3/4. So this is my new upper limit because this is my upper limit for x. And this is my new lower limit because of my lower limit for x. Okay. Now, because we've changed to bounds for theta, we never have to go back to x the way we did using that triangle. What we have is the integral from 4 to 6 of this expression here is equal to the integral from the arc cosine or inverse cosine of 3/4 to pi over 3 of 9 times secant cubed theta d theta. And the antiderivative of this is something that we calculated earlier. It turned out to be 9/2 times secant of theta times tangent of theta plus natural log of secant, the absolute value of secant of theta plus tangent of theta. And then we can evaluate this from our lower limit to our upper limit. Okay. So at our upper limit, we have this. And at our lower limit, we have this. Now this one's a little less clean, but all of these can be simplified, and I'll show you how. Now, if you're thinking to yourself, I'd rather do it the other way, that's totally fine. Okay, so now let's evaluate these. We've got secant of pi over 3 and tangent of pi over 3. Well, just looking at this triangle, we can find the secant and tangent of that angle. Secant of pi over 3 in this case, this is our angle pi over 3, is a hypotenuse over adjacent. So it's 2, which is what we would expect because cosine of theta is 1/2, so secant of theta should be 2. And tangent of theta is opposite over adjacent, so we have square root of 3 there. So we have 2 and a square root of 3. So this is 2 and root 3, and this is a 2. Oops, not here on that line, it's going to be down here. Sorry about that. This is 2 and root 3, and this one is 2 and root 3. Okay, so now we have to find the secant of this inverse cosine and the tangent of this inverse cosine so that we can substitute those in. It looks much worse than it is. The inverse cosine of 3/4 is just this angle theta. So if we find the length of the third side of this triangle, we can use this triangle to find the secant of theta and the tangent of theta, which is the secant of the arc cosine of 3/4 and the tangent of the arc cosine of 3/4. If I call this side length b, 3 squared plus b squared is equal to 4 squared. So b squared must be 16 minus 9, which is 7. So b equals the positive square root of 7. Okay, great. So now that means the secant of the arc cosine of 3/4, just the secant of this angle theta, well, that's hypotenuse over adjacent. Well, we already knew that. It's reciprocal of cosine, so it's 4/3. And tangent of that angle is opposite over adjacent. So square root of 7/3. And you see a square root of 7 there, you see a square root of 7 there. That's a very good sign. It means we're probably on the right track. So secant is 4/3, not 3/4. And tangent is square root of 7/3. Okay, so that's our answer. It's just not simplified. Let's see if it simplifies to the other answer. So we've got 9/2 times 2√3. Actually, I think I'll get rid of those parentheses there. Or we'll just keep them there for that first expression. And then distribute that 9/2 to both of these terms. So of 9/2 times the natural log of 2 plus the square root of 3 from right there. Okay. And then down here we have minus 9/2 times 4/3 times the square root of 3, or square root of 7/3 is 4 square roots of 7/3 times 3, which is 9. So those 9's reduced. The 2 goes into the 4 twice. And then don't forget to distribute that 9/2 again. So we've got negative 9/2 times the natural log of 4/3 plus the square root of 7/3. That's 4 plus the square root of 7/3. Okay, so these 2's reduced. Now we've got 9√3 here plus 9/2 times this log minus 9/2 times that log. So we can write that as one expression like this. And then we've got minus 2 times the square root of 7 right there. And then this I can think of as a log of A minus log of B. And we know that log of A minus log of B is log of A over B. So we've got 9√3 minus 2√7 plus 9/2. If I'm doing this divided by this fraction, I could just multiply by the reciprocal. You see it? I hope you see it. If we distribute that 3 there, obviously this is for a different problem. Oops, there should be a log there. We have 9/2 times the log of 3 times this expression is 6 plus 3√3. And then we've got 4 plus √7 in the denominator. So that is the answer that we get when we substitute those limits, which is the same as the answer that we got when we didn't substitute the limits. Now, wait a minute. Nope, it's exactly the same. I thought there was a sign difference, but there wasn't.